So in the last video, we talked about how to determine the polarity of molecules in 3 dimensions. In this video, we'll talk about how the polarity of molecules affects the intermolecular forces, the forces that exist between molecules. So let's go ahead and draw a picture of two molecules interacting, and let's see if we can figure out the intermolecular forces that exist between those two molecules. So here I've drawn one molecule of acetone, and if I'm going to show the forces that exist between molecules of acetone, I need to go ahead and draw two molecules. So here I'm just putting the last CH3 group on my second acetone molecule. So, what is the polarity of an acetone molecule? So, we know from our previous video that oxygen being much more electronegative than carbon, oxygen will pull the electrons in the bonds between oxygen and carbon closer towards it, so it will induce a charge, right? So my induction vector shows the movement of electrons between my two atoms. So if these electrons move a little bit closer to oxygen, oxygen has a little bit more negative charge around it, so it gets a partial negative charge. Carbon loses some of the electrons that were around it, so it ends up being partially positive. The same situation happens down here. Oxygen will be partially negative, carbon will be partially positive, so we've created a polarized situation. And we know that opposite charges attract, right? So if this partially positive carbon gets close enough in space to this negatively charged oxygen, there's going to be an attraction between those two atoms. And the closer those two molecules get, the stronger the force of attraction, according to Coulomb's law. So there's an electrostatic attraction between opposite charges that helps to hold those acetone molecules together, and we say that is an intermolecular force. Since our top acetone molecule is polar, and our bottom acetone molecule is polar. Each one of them has a dipole moment, right, due to those opposite charges. So we have one dipole interacting with another dipole, so we call this dipole interaction. So dipole interaction is an intermolecular force, a force that exists between molecules. So how does an intermolecular force differ from an intramolecular force? An intramolecular force is the force is the force within a molecule. So what would be the forces within a molecule? Well, that would be, of course, the chemical bonds, right? So if I go ahead and circle that covalent bond, that's an intramolecular force. That's a force holding the molecule together. So intramolecular forces are the forces within molecules, whereas an intermolecular force is the force between molecules. An intramolecular force must be stronger than an intermolecular force because the molecule has to hold together, right? If an intermolecular force were stronger than a chemical bond, then the whole molecule would be pulled apart. So this is an example of dipole-dipole interaction, which is one type of an intermolecular force. Let's look at two other molecules, and let's see what intermolecular force exists between them. So let's do two water molecules. So if I go ahead and draw one water molecule like that, and then I have another water molecule down here, I know that water is a polar molecule because this covalent bond between oxygen and hydrogen is polarized. Oxygen is more electronegative than hydrogen, so it will pull those electrons closer to it, giving it a partial negative, leaving the hydrogen with a partial positive. And the same situation exists on the bottom water molecule like that. So we can see that if these two water molecules get close enough together in space, right, there will be an electrostatic attraction between the partially positive hydrogen on one molecule and the partially negative oxygen on the other molecule. And since we know that water is a polar molecule, and we know that is polar, we know that is polar, we might expect this intermolecular force to be another dipole-dipole interaction. And in fact, this is another type of intermolecular force. It's actually a stronger form of attraction. It's actually a stronger form of dipole-dipole interaction, and we call this hydrogen bonding. So this is an example of hydrogen bonding, which is just a very strong dipole-dipole interaction, a special type of dipole-dipole interaction. And what is happening in hydrogen bonding? Well, we can see that a hydrogen is being shared between two very electronegative atoms. So let me just focus in on what is happening here. We can see that hydrogen is bonded to one oxygen in one molecule, and then it is interacting with the oxygen of another molecule. So the trick to hydrogen bonding is you must have two electronegative atoms involved. If you don't have two electronegative atoms involved, it will not be hydrogen bonding. So let's refresh our memory about the most electronegative atoms on our periodic table. Right, so we can take a look at all of the atoms that students memorize for hydrogen bonding, right? The mnemonic is phone, right? So here is fluorine, the most electronegative atom, followed by oxygen, and followed by nitrogen. So those are the three electronegative atoms that could be bonding with hydrogen, right? So the electronegative atoms that would take the place of oxygen in another example of hydrogen bonding. So phone is the mnemonic to remember. And some students will say, well, why not chlorine? Why could chlorine not contribute to hydrogen bonding? It has an electronegativity value of 3, and so does nitrogen. Nitrogen also has a value of 3. So the answer to that question, according to Linus Pauling, is the size of the atoms. Nitrogen, oxygen, and fluorine are all in the second period of the periodic table, so they all have similar sizes, whereas chlorine is one period down, so it has a much larger size. And that larger size prevents chlorine atoms from getting close enough to the oxygen atom. And that is the reason why chlorine is not observed or not considered to be an example of hydrogen bonding. So Linus Pauling also talks about why the name was originally hydrogen bonding. This interaction was so strong that at one time this was actually considered to be an actual bond, right? So at one time this bond right here, which we call now an intermolecular force, at one time chemists considered this to be an intramolecular force. So hydrogen would be forming two bonds between two different atoms. And now we know that that is not true, but the name has stuck, right? So we still call it hydrogen bonding, even though it is not an intramolecular force. It is actually an intermolecular force. Let's look at another example of an intermolecular force. Let's look at two molecules of methane, right? So methane being CH4. Right? Well, we know from our previous video that methane is a non-polar molecule. So if methane is a non-polar molecule, that means there will be no dipole-dipole interaction between these molecules, and there will be no hydrogen bonding interaction between these two molecules. So what is it that's holding these two molecules together? Well, if I think about the electrons right here, the electrons in this bond, according to quantum mechanics, those electrons are always moving around in orbitals. So maybe for a transient moment of time, those electrons might end up a little bit closer towards the hydrogen, giving the hydrogen the tiniest partial negative charge. And then on this molecule on the right, maybe the electrons in this bond end up being a little bit closer to carbon for a transient moment of time. Well, that would give this hydrogen a partial positive charge, right? So for very, very, very brief moments of time, you could consider this molecule to have a partial negative charge on it and this molecule to have a partial positive charge on it, and so opposite charges attract. So there could be a form of electrostatic attraction between my two molecules. And we call that form of attraction a London dispersion force. So London dispersion interaction, named after the scientist London who came up with this concept. So even though this is a nonpolar molecule and this is a nonpolar molecule, there is a force that is causing these molecules to stick together, and that is London dispersion forces. So London dispersion forces are found between all molecules, not just two nonpolar molecules. Polar molecules will exhibit London dispersion forces as well. But because these interactions are so transient and such small charges, these are the weakest of our intermolecular forces. So let's just quickly sum up the order of strength between our intermolecular forces. All right, the strongest intermolecular force is hydrogen bonding. And because of this, hydrogen bonding is extremely important in organic chemistry and biochemistry. That is followed by dipole-dipole interactions. And we've just seen how the weakest intermolecular forces are the London dispersion forces. So, in the next video, we will see how these intermolecular forces affect the physical properties of molecules.